Hi, today we're going to be talking about the application of calculus in medicine, more specifically focusing on how calculus is used to estimate the growth of a tumor. But first we have to know, what is calculus? Calculus is the mathematical study of change. It is the mathematics of velocity, acceleration, and more concepts. Calculus is mainly divided into two branches, differential and integral calculus.
How calculus can be used in our daily life? Well, calculus enables engineers, scientists, doctors, and economists to model real-life situations and predict upcoming results.
As we previously said, we are going to emphasize calculus into the world of medicine. Medicine is a field of life science that highly depends on calculus as a technique to analyze different aspects.
There are so many ways where calculus can be applied to medicine, but some examples of calculus being used in medicine can be to measure the blood flow, cardiac output, tumor growth, and determination of population genetics, among many other applications in biology and medicine. Also, mathematical models have played a huge role in medicine research. The modeling study may provide clinicians important insights on radiation therapy strategies through identification of biological factors, and thus significantly modifying the effectiveness of the treatment. Now that we know how calculus is related to medicine, we will explain you the model for tumor growth.
What is a tumor? A tumor is an abnormal growth of body tissue. It is a mass of tissue that's formed by an accumulation of abnormal cells. Normally, the cells in your body age, die, and are replaced by new cells. With cancer and other tumors, something disrupts this cycle. Tumor cells grow even though the body does not need them. And unlike old cells, they don't die. As this process goes on, the tumor continues to grow as more and more cells are added to the mass. The cancer cells grow and divide to create more cells and will eventually increase the size of the tumor. Inside each nucleus, genetic material called DNA contains the instructions for directing this cell division process. Normally, the DNA responds to damage by either repairing itself or instructing the cell to die. In cancer, however, when these sections are damaged, the DNA is unable to repair itself, and instead, the unpaired DNA causes the cell to grow and divide uncontrollably. A tumor forms as the cancer cells multiply and accumulate. Since cancer cells do not stick together as well as normal cells, they may break away and enter a nearby blood vessel. Cancer cells in blood vessels may travel to other areas of your body and form additional tumors.
There are many models to calculate the growth of a tumor, such as the Terra model, the logistic model by Verhus, the Comster law, and the model that we're going to talk about today, exponential growth and decay. Since a tumor is a cell population, growth and decay model explanation. This equation tells us that the population grows at a rate that is proportional to the size of the population. Here, the population growth rate is how fast the population is growing at a certain time. In our equation, T is equal to the relative growth, P is equal to the size of a population at a given time, and if our population increases, the division of the derivatives will also increase proportionally.
So for our first step, we're going to multiply both sides by dt. We then go and divide by p. We integrate both sides. Where c is the general constant, then we raise them on both sides. After a logarithm is 1, so we only remain with p on the left side. Multiplication of exponents with the same base equals the sum of the exponents. E to the c is a constant, so we can replace it with c. Multiplication is equal to equation 1.
When we substitute t with 0 in the equation, k times 0 is equal to 0 and e to the 0 is equal to 1, so we only remain with t. So p0, the initial population, is equal to c, the constant. We put all this into the first equation and we get that the population is equal to the initial population, p0, multiplied by e raised to the k times t, which are the relative growth rate and time. Now, we can use this formula to determine the size of a population in a specific time or predict the size of the population.